Swayam Prabha. Digital India. Educated India.
Hi, so welcome back. So where we stopped in the last class was looking at the pressure, right? The pressure derivative or pressure gradient, right? In a boundary layer which we are considering as turbulent, right? And this is where we had stopped, right? And we said that if you basically the pressure gradient in the x direction, in the actual direction, is essentially the mean pressure gradient on the x direction, and we found that that actually is equal to we define something as Pw, right? So Pw, which we basically, what is Pw? Essentially Pw is the pressure at the bottom wall, right? So W essentially represents wall. So yeah, well, I haven't written that here. So essentially Pw is essentially the so if you see here, okay, so mean pressure gradient, okay, across in the x direction is essentially the pressure gradient of the wall pressure, right, gradient, and this is uniform across the flow, and which is what I was looking at here, okay, which is what I was looking at here. So that is constant over a particular x, okay. All right, now so we started doing that using the x momentum in the y direction. So we looked at this equation. We started looking at the mean momentum equation in the y direction. From there, we got information about the pressure gradient. So we're going to use the same thing, right? And now, so we got this sort of information. Now, what we'll do is we'll take the mean momentum equation in the x direction and talk a little bit about shear stress. Okay, all right. So let's do that. So there we go. All right. So we're going to talk about, say, mean momentum equation. In the x direction, okay. So we'll write that as so I'm writing d here instead of a partial, right? That's because this is a gradient. If it exists only in the x direction. There's still gradient in the y direction. It's constant, right? We've seen that. Okay, so that's what we sort of did with the y momentum equation. That's what we showed in the y momentum equation. It's a uniform pressure gradient in the y direction, and this is for a turbulent case. If it's a laminar boundary layer, then actually it is 0. Okay, so therefore the pressure, the free stream pressure, is actually imposed onto the boundary layer. Okay, all right. So that's that. Okay, and this, well, this is essentially okay, that where if I write this like this, okay, where tau right? Okay, so essentially, so I took these two terms out here, okay, and also I replaced this by this. This is also something that okay, I haven't proved this, I guess. So this is central line velocity, and you can actually prove this. The pressure gradient is actually equal to this. So this is fine. Okay. All right. So now the tau is what I did here. Okay. So this is the term, right? This is the term. So I can also write this, right? I can also write that as nu del del y of, right, minus del del y of u dash v dash this, right, and that is why we decide we actually so that's how we define the tau. So if you take basically a derivative of, so del tau, so 1 by rho del tau del y, okay. Okay, so that's basically our mean momentum equation in the x direction. Okay, so what I'm saying is you could just cross check. So you could take a derivative of this. You could take a derivative of this, multiply that by tau, and see if we get back this. If we take a derivative of this tau, right, multiply that by 1 by rho, and cross check whether you get back this whole thing. Right. So that whole thing is something, and if you break it up, and so I wrote this, okay, like this. Okay, that's all. So essentially, I mean, the thing is that you could just yeah. So okay, you could just sort of write that. Okay. All right. So this you could do this. Okay. So you could sort of do this here. You could do this. Del del y of nu isn't it, that, okay, and then you multiply both these terms by a rho, so that you multiply this by 1 by rho, right. So see if, so then what you see is that this term, right, is actually equal to this. So this is actually equal to tau. Okay. So then 1 by rho del del y of tau is this term. Okay. So you can just cross check that essentially. Okay. Now let us look at this. Equation should also mean something, because we are just putting expressing a physical phenomena in with equations or mathematically, so that we can calculate, we can design, we can build things, right. So equations are not just mere numbers or variables put together. They should mean something, right. So, and I make sure that I understand, and some of the math can actually get to me, but at least I need to understand what is going on there. Okay, it takes a while, it takes work, but you should sort of try to do that. Okay, my suggestion is you should try. Okay, so now at the wall. Okay, now let's look at the wall. What happens at the wall? Okay, when I say at the wall, I basically mean that at basically y is 0. Okay, so we're looking at basically the flow across a boundary layer, or flow on a flat plate, right? This is my y, this is my x. So this is that y is equal to 0, right? So at the wall, that's what I mean by wall. So y is actually equal to 0. Okay. Now, what happens at the wall? Well, the convective terms will be 0 because the velocity itself is going to be 0. Okay. Now, at the wall, so therefore, okay, let me sort of write that down again, or what? Okay. So if you see, let's take a case. Okay. So let's take a case. Let the pressure gradient, right, also to be equal to 0. Let that be 0. Okay. But we mean these are anyway equal to 0, or these are equal to 0 at, right, that is at the wall. Okay. So what you're essentially then, what you will be on the right hand side, if you see, right. So what you are, so pressure gradient is also 0. Okay. Now then what do we get? Okay. Centerline velocity, well, del u naught del x, that's anyway going to be, okay, actually this is, sorry, I made a mistake. Okay, so this is actually the free stream velocity. Okay, free stream, well, which in this case is the centerline velocity. So I think that is okay. Sorry, what I wrote earlier is fine. Okay, this is okay. All right, fine. Now, so if I look at this equation, the momentum equation, so I'm looking at the equation here. Okay, so 1 by rho del tau del y, which is fine, right? So at the wall, these things are 0. So at the wall, the flow is essentially 0. So these are also 0 because essentially the flow itself is, come to a stop there. So that term will also go to 0. Okay, and of course, this. Okay, then. How does this, and this is of course the central line velocity, which again at the wall this, yeah, so what does that mean at the wall? At the wall it doesn't mean anything, right? Okay, so the convective terms basically are all 0, okay, at the wall. So at the wall anyway there is no, this is anyway central line velocity or something, right? So u naught is essentially u free stream. Okay. Okay, I think I'll have to cross check that. Okay. Now then what happens here is that, so therefore what we can say here is that nu, okay, that is at y is equal to 0. Okay. There are no other terms here. So that is equal to, that is that y is equal to 0, right? And the left hand side, as you can see, is equal to 0. So all of that is equal to 0. Okay. So in that case, now what we had written earlier, okay, what we had written earlier is that right. So what we had, okay. Now from previously what we had done is that this del 2 y bar del y 2, right. So del 2 y bar del y 2. Oh, okay. So at the wall this is equal to 0. Okay. Right. Now if at the wall this is equal to 0, okay, then let us say if at the wall this is equal to 0, okay. Okay, So from this, okay, so let's just say now then, and we've proven earlier that dp dx is equal to d dx of, right, this is the wall pressure. That is now from, therefore, in the mean momentum equation, right, mean momentum equation in the x direction, what we get there is del tau del y, right, is equal to right. So I'm going to call that as, well, equation 2, whatever. So I don't know if I wrote that as 1 yesterday, okay, in the last class. So dpw dx, okay. Now, so the inference here is there is no mean acceleration, there is no mean acceleration, okay. The left hand side of that equation is cross stream shear stress, okay. So cross stream shear stress gradient, and the right hand side is axial normal stress gradient, normal stress gradient. What am I talking about? So the left hand side is this, right, the delta. So this is the cross stream shear stress gradient. Cross stream meaning, so this is a shear stress which is basically when you consider the flow to happen in layers, and that is the stress between the layers of fluid as they try to move over each other, right. That's the shear stress we're talking about. So that is a shear stress which is, varying across y direction, right. So therefore cross streams, the stream direction is x direction, so this is cross stream, or in a direction which is normal to the actual direction or direction of flow, what have you. So cross stream shear stress gradient, and the other is the axial normal stress gradient. This is the right hand side. So this is the wall shear stress. So axial normal stress basically. So now this is the pressure which is imposed onto the boundary line, right. So this is what we part for here. So furthermore, we can write a little bit. Now tau here is a function, right. Now let's just say from here, tau is a function, okay, of only y, right, and pw, right, is a function of only x, right. So if this has to be, so if this is really true, right. So essentially if this really is going to hold, then this is going to be a constant, right. This is going to be a constant, and of course wall shear stress, right. So therefore, yeah, well, wall shear stress T at y equal to 0 is tau wall, right, which is equal to, yeah, so that is essentially, we can call that as tau wall, okay. Now wall shear stress, okay. Now the wall shear stress, which is tau wall, right, and the viscosity, right, these are important parameters. So tau wall and the viscosity, right, viscosity is important parameters. Now what we wrote previously here is the total shear stress, total stress. So that was a combination of this is the viscous stress, as you can see here. This part is the tau. This is the viscous part because you have the viscosity coefficient there, and this is the Reynolds stress, right. This is the Reynolds stress, and so the total stress is a combination of both, right. Is a combination of both. Now at the wall, however, right? We've shown that, right, at the wall, which is basically y tends to 0. So, the fluctuating components of velocity are 0, right. The convective terms of the fluid are 0 at the wall. If this is 0, right, then this part, the Reynolds stresses are also 0, which means the total stress is dominated by the viscous part, viscosity of the fluid at the wall, right. So, I think we should write that. That is an inference we can sort of, easily make, right. So, right. So, at the wall, okay, at the wall, shear stress, okay, shear stress is entirely contributed by the viscosity, right. And so, right. So, it's at the wall, the shear stress is essentially totally due to the viscosity, right. And now this becomes important. So, that means that throughout the flow, we have yet another little distance or another little length along near the wall, where the shear stress is entirely contributed by the viscosity, which means that we would help us rather, right, to define different length scales and velocity scales for that region, right. So, and which we will use, which will pertain to only that region. So, which is what we will proceed to do. Okay. So, essentially when we wrote, so we started out with the mean momentum equation, right, in the x direction and y direction, and then we wrote down this equation, and then we saw that this is tau. Now, this tau is nothing but the total stress, which is contributed. There is a viscous contribution and there is a Reynolds stresses, but at the wall this is going to go at the wall, basically this is also going to go to 0, right, the Reynolds stresses. So, this is entirely contributed by the viscosity, right. So, now when I say y tends to 0, y is nearly 0, right. So, what is that length scale, right, if the where the shear stress is negligible, right. So, we will proceed to do that. We will proceed to define length scales in that near wall region. So, what we basically say, this is the near wall region. It's a near wall region. Okay. So, we have something called a friction velocity. Okay. This, right. Then we have a viscous length scale. So, friction at the wall, right, it's, I mean, shear stress at the wall, tau wall. Okay. Then this viscous length scale we define as, okay, so this is essentially equal to this. Okay. Then we define something called a friction Reynolds number. Okay. So, R E tau is equal to U V, sorry, right. So, this I can write as U tau. This thing is equal to, as you can see. So, if you can from here, if you see, right. So, nu 1 by nu, okay. So, I can use this from here, okay. Or you can, okay, actually not that. Okay, so you can actually see from here. So this one, okay, this one, and this, if you see. So u tau I can replace by nu by. So from there, actually, I will write this is equal to. Okay, that is actually equal to delta by delta v. So if you see u tau, okay, this one this is equal to nu by delta v. That's all I did. So therefore, that cancels out, and this is what we get. Okay, I'm just not writing it. That's all. Okay, so now, so that's that. Okay, this is interesting. The Reynolds number is actually equal to the a ratio of the boundary layer thickness to the viscous length scale. It's interesting, right? Now, distance from the wall, okay, then distance from the wall, okay, measured in viscous lengths okay, or wall units. Okay. So, which is that equal to, okay, I can do that, and that again is equal to right. So, u tau into y by nu, that's also equal to the same. So, this is distance from the wall measured in viscous length or wall unit. So, I call that as y plus. Okay. So, now we come to something which is called the law of the wall. Okay. So, we are going to write that the law So, essentially in the near wall region, what we have done here is come up with several length scales, right, several of these okay, several of these length scales, right, which are applicable in the viscous portion, right, of the boundary layer, right, which we are defining as delta V. Okay. What does the law of the wall say? Okay. Now, at high Reynolds number close to the wall, right. So, which is essentially saying y by delta, right. There is an inner layer, right, in which the mean velocity profile okay, is determined by the viscous scales independent of delta, boundary layer thickness, and free stream velocity. Right. This is interesting that at high Reynolds number close to the wall, okay, there is an inner layer. There is an inner layer in which the mean velocity profile is determined by the viscous scales, right, independent of delta and u infinity. Okay. Now, this was actually proposed. This was actually proposed by Prondl in 1925. This is credited to Prondl in 1925. Okay, I'll do a little bit of little more. Okay, before I do a little more math, because I guess it's getting a little boring, right? So let me just say. So now, what exactly are we talking about here? Now, we didn't talk about these things when it's a laminar boundary layer. We said there is a boundary layer, right? On the upper part of the boundary layer, there is the limit at which you reach the free stream velocity, and there again the effect of the dominance of viscosity is negligible, or the effect of viscosity is negligible. So viscosity effects are dominant within the boundary layer, and we can figure out what length this the boundary layer thickness can be, right? And for example, to give you say about 128 meters, I think I did a problem in my class. So 128 meters of a flat plate, the edge, the boundary layer thickness, right, at the end of the plate is about an inch, right. So that's how those scales are. Now we're talking about that. So that's for a laminar boundary layer case. Now we are talking about a turbulent boundary layer case, and where we find that there are even further length scales, as we saw previously for the round jet. So again, there are length scales within that boundary layer, which is near the wall, and which is a little more than just near the wall and the edge of the boundary layer. Okay, so in that context, let me just try. So we came up with scales, right? We came up with scales like this, right? So distance from the wall is measured in terms of viscous length. So then we said, a viscous length scale is defined as delta V, and that is that. And then we define a friction velocity, a friction Reynolds number, hence a Y plus. Okay. So now let me give you some numbers. This is based on research, etc. Now, if Y plus, right. So again, let me go back. What is Y plus? Y plus is Y by delta V. I think we should write that. Okay. So this one is actually, so this is the viscous length scale that we've defined. Okay. So if this Y plus, okay, is less than 50, okay, then if that is so, then direct effect, okay, of molecular viscosity on shear stress. Okay, and this is then called the viscous, this is called the viscous wall region. Okay. Again, if Y is greater than 50, direct effect of viscosity is negligible. So direct direct effect of viscosity is negligible, and this layer is actually called the outer layer. This is the outer layer. Okay, and finally, we have Y plus is less than 5, right? Here, Reynolds shear stress is negligible compared to the viscous shear stress. Okay, this is like really close to the wall. So now we have some idea about how when I say close, it's only mathematically nice to write Y is equal to 0. Okay, so but we are really there's no like strict demarcation that how much is near wall is near the wall. So if I'm really at the wall or just about at the wall, a little bit around the wall, I mean, give me some numbers, right? That's what we're trying to do. So if this y plus, right, is less than 5, okay, then Reynolds shear stress, okay, is negligible, right, and the viscous shear stress dominates. So viscous shear stress is dominant, right, and this is essentially called the viscous sublayer. This is the viscous sublayer. Okay, this is so. Therefore, now that we define some length scales, for the boundary layer, where the viscosity effects and the Reynolds stress effects, so are not, they're not working together. So if the length scale is such where it is 5 times less, it is less than 5 times of the the viscosity length scale, then there the viscous shear stress is dominant and the Reynolds shear stress is negligible. As a result, this is basically called as the viscous sublayer. Okay, all right. So now let us do a little bit of math. Okay, let us do a little bit of math and let's see. Now, as we've been discussing, so the parameters which completely sort of define the flow, right? So parameters that define the flow right? What could they be? Density, viscosity, length, right? And let's just go back. So this is your u tau, right? So these are things which basically define your flow, right? So now let us just write. Let us just come up, okay, with a function which looks like this. So let us say that. Okay, so let's just say, so because this is needed to understand how the stress is behaving, etc., near the wall. So if at different length scales, so that's what we are trying to sort of do here. Okay, so we're going to write this. I'm trying to develop this in such a way that I can actually include sort of all the cases in one equation. So because here what is happening is, so if you look at the equation, here, yeah. So if you look at this equation here, now that I have a tau here, okay. Now this tau, however, is a combination of both of these, right? But then both of these parameters, both of these parts of the shear stress do not act at all the length scales, right? So some of it is acting up only when it belongs to y plus is of a certain number, or y plus is a certain less number. So if y plus is less than 5, this part is not going to be there. This tau is going to be there only for this, right? Now mathematically that has implications, right? If this part is gone and only this part is there, else sometimes both are there, sometimes this is not there and this is there. So we're just trying to see if mathematically we can do something where we write this out in a slightly using one variable, something like that. So let's just say, so this one is, say, by y, and let's just say this is a function, right, which is this, or y plus essentially, right. So, let us just say this is this you know, it's just a non-dimensional function, that is all. Okay. So, this phi 1 is a non-dimensional function. Okay. Now, then we know that y plus is by that, okay, and this we know this. Let us do some math and then we can discuss, right. Okay. So, this equation, so therefore, now then we write this as, so d dy, okay, u mean, right. So, u mean is actually equal to u plus and u this, correct? You get that from here, is that fine? Okay, is equal to right. So, this is essentially from here. So, I replace y by this thing by y plus, which is what I get here. Okay. So, then we just take the derivative. So, let us just say this is right. Okay. This is equal to that. Okay. Now, u tau is actually equal to this, right. So, this is tau wall. Okay. Therefore, is what? Is equal to 0, right. So, we are taking the variation of tau at the wall, tau at the wall. This is actually equal to basically taking the d dy of tau wall. So, tau wall is equal, this is equal to 0, right. Tau wall is a constant value. So, it does not differ along in the along y axis. Okay. So, therefore, taking derivative along the y axis of u tau, which is actually a function of tau wall, is actually equal to 0. Okay. In that case, therefore, right. So, which means this, right. So, then what do we have? So, therefore, u tau, okay. Okay. Now, that is equal to this, okay, or so in that case here these two will cancel out, okay, they cancel. So, then shall we, okay, I am not going to go to the next page, okay. So, I am going to just continue here, okay. Then, so or right, this, okay, then or y by delta phi, okay, is y by delta phi, okay. So, or du this is equal to this, right. Now, that is an important result. That is an important result. Okay. Now, then let us integrate it. So, then u plus actually, so u plus is actually an integral right, and this is something that I am going to call as function of the wall, which is a function of this. I am going to just call that as, you know, this integral, this whole thing. Okay. So, u plus is essentially that. Now, using that, so now if I use that, okay, now let's look at the viscous sublayer. Okay. If I look at the viscous sublayer, now from the no slip condition, now u, okay, at y is equal to 0. Right, this is the mean velocity at the wall, okay, viscous sublayer, which is equal to 0. Viscous sublayer is, let's go back. Where is the viscous sublayer? So this is the viscous sublayer. This is the viscous sublayer, which is this, right? So where y plus is essentially less than 5. Okay. Now in the viscous, so now we're talking about the viscous sublayer. So no slip condition, right? Which means that this is equal to 0. Okay. Now this means that u plus, right, which is equal to u mean by u tau, right, okay, and this is equal to right. So this actually again, so if I go back to the previous thing, so if you see this, what is u plus? So what is, so this is your u tau, okay, this is your u tau, okay, so and this is your y plus, okay, so this is essentially the relationship. Might want to cross check that, okay. So if the no slip condition is equal to 0, you know, it essentially implies that u plus, right. So u plus, which is, you know, the mean velocity by this, and which is also equal to Fy, okay. So this is also equal to 0, right. So this is also equal to 0, okay. Now we wrote down what is f, what is f. So the f is essentially this function, okay. Now let's just say take a Taylor series expansion, okay, Taylor series expansion of this function, right, when is small, right. So then f okay, if I expand that, so that is going to be this, etc. Okay. So then if, right, this, then which means that now f w y plus is actually equal to y plus if I ignore the higher order terms, which means so if I, which means this, right, this is basically ignoring higher order terms, okay. So essentially f w, right, this is equal to 0. Now that So, Fw y plus is actually equal to y plus. Okay. So, therefore, u plus, okay, is equal to Fw y plus, right. Now, at the wall this is equal to 0, which is fine, right. So, at the wall this is equal to 0. Now, this u plus is this, right, and that is actually a, so which is actually a linear relationship. So, this is essentially a linear relationship, right. So, u plus is actually equal to y plus, right. So, then du plus dy plus, right, is equal to 1. Okay. So, this is something that is important. This is happening in the viscous sublayer. Okay. Now, I will do a few things. So, then there is this was the law of the wall, right. So, the law of the wall, we said that things are a little different, very close to the wall, you know. Now, and we said it is different, and then we defined some viscous length scales, which is something like this, right. So, this is the viscous sublayer that we are talking about. This is the viscous wall region, right, and this is the viscous sublayer where only viscosity, even in a turbulent flow, only viscosity effects are dominant, turbulent regions are not. Okay. We did that, and then we are trying to figure out some numbers, etc., etc., and what we have figured out here in the viscous sublayer, right, no slip condition, this and that, right, we have figured out that u plus, okay, is actually equal to y plus, and it is a linear relationship, and u plus this is 1. Okay, this is the viscous sublayer. So, we will discuss this a little further in the next class. I will stop for today. Thank you.